All right, so welcome to lesson 1 of unit 2. This is looking at R9, arithmetic sequences and series. So 1.1 looks specifically at sequences. So the first thing we need to know is what is a sequence, and that is specifically any data that produces a pattern. Okay, so events that produce data that forms a pattern. Now we're going to be looking at two main types of sequences in this class, arithmetic and geometric. So our first outcome, R9, is strictly about arithmetic sequences. So an arithmetic sequence is actually specifically when we've got consecutive terms that increase by a constant number. So we see that in 2, 4, 6, 8, 10. It's increasing by a consistent amount every time, and specifically that consistent amount is being added. Okay, that difference, that amount it's changing by, is called the common difference. So when we look at this pattern, we can identify this key information. The first term is known as T1. So usually we start, so we're starting counting at 1, 2, 3, 4, 5 in terms of our term numbers. So our first term is 2, and our second term is 4. To find the common difference, what you do is you take the difference between those two numbers, specifically your second term, subtract the first term. So TD equals T2 minus T1. You could also figure it out by doing T3 minus T2. So in general, you could say your difference is term n plus 1 minus term n. In this particular example, the difference here is positive 2. The dots at the end of our sequence, and we see it showing up in both scenarios, no matter which way we write it, indicates that the sequence goes forever, continues forever, so it is known as an infinite sequence. Okay, all arithmetic sequences are infinite sequences. Okay, because we can keep adding 2 forever, no matter what. There's always room to add 2. Okay. This particular sequence is known as an increasing sequence. Okay, so it can be, it's going up, but it can also be decreasing, going downward. So an increasing sequence, like we saw here, is where our D value is positive. So in this case, we are adding a quarter every time. Okay, and again, I can figure that out by looking at the difference between any two terms. Okay, so I chose those two because it's the most obvious what fraction I'm actually adding here. A decreasing sequence can be still positive, but the key thing is that the D value, our common difference, is negative. So we've got 5 is my term 1. That is positive, but this is a decreasing sequence because we are heading into the negatives. My value decreased specifically by 6. So negative 6 is my D value. So how do we kind of talk about this? Well, given the sequence 10, 16, 22, 28, what can you already tell me about it? Well, it's increasing. Its D value is 6. And because I'm adding the same amount every time, it's an arithmetic sequence. So I've already got 3 key pieces of information. You could also tell me term 1 is 10. Arithmetic. My common difference is positive 6, so it's increasing. So we've already got the gist of it. Well, how can we express this as like an equation? How can we eventually get to that point? Well, first of all, we look at our terms. So 10, 16, 22, 28. Infinite sequence, ... So, but we're only going to look at the first 4 terms here. Well, what about if we always try and link it back to that first term? Well, how would we, and we can talk about it in terms of d, and remember d is positive 6. So how would we go from 10 to 16? Well, we would add 6. And how would we go from 10 to 22? Well, we would think, you could either say you could add 12, or you could describe it as 10 plus 2 times 6, or 10 plus 6 plus 6. Our fourth term then becomes, well, you could think of it as 10 plus 18, but really that's the same as 10 plus 3 times 6, or 10 plus 6 plus 6 plus 6. In general, if 10 is term 1 and d is d is my common difference, and I can count how many times I've actually added my common difference, well, maybe I can make a link here. So 10 is term 1, done. Term 2 can actually be written as term 1 plus d. Term 3 is going to be term 1 plus 2 d's. Term 4 is going to be term 1 plus 3 d's. Are you noticing a pattern? How many d's? Is there like an algorithm? Is there a way I can always know how many common differences I need to add in order to get my next term? Well, 3 d's are getting added when it's term 4. So just to kind of make a note on the side here. Okay, so number of d, common difference, and term number. So we can just call it n. So if it's term 1, I'm not adding any. If it's term 2, I'm adding 1 d. Term 3, I'm adding 2. Term 4, I'm adding 3. So in general, I'm adding 1 less than my term number. And that's actually where my equation finally gets us to. So in general, what we can say is that for any term number, no matter where it is in my arithmetic sequence, I'm going to take my original term number and I'm going to add 1 less my term number times times my common difference. Okay, so this is what all these different variables mean down here. And either way, both of these are our equation. So whichever way you like to look at it. So let's apply these. Well, in general, we're just talking about increasing arithmetic sequences. So you could literally choose any number. We can even start in the negatives. If we start at negative 10, and we are going to actually be increasing by a half, then this would be negative 9.5 and negative 9. Negative 8.5, negative 8. Negative 7.5. And that takes me to my 6 terms, so I can keep going forward. The decreasing arithmetic sequence, again, can start positive. It can also start negative. I'm going to start negative just so we get a little bit more comfortable with integers. So if I start at negative 2, and I decrease by 5 every time. So here my d value was positive 0.5. D value here, my common difference is going to be negative 5. So that becomes -7, -12, -17, -22, -27, and it keeps going forever. So always put those dot dot dots at the end. You must include those because they are infinite. Example 2, for the sequence 3, 10, 17, and 24, continues forever. Determine term 15. Well, we know term 1 is 3. We also know our equation tells us that for any term number, we're going to take term 1, we're going to add 1 less our term number times our common difference. So n in this case is 15. My common difference, I look at my equation, it's changing by +7, +7, +7. So I'm confirming, yes, in fact, this is an arithmetic sequence. I am going to be using this equation, and my common difference is +7. Well, now I have everything I need to be able to fill this in for term 15. Take 15 minus 1 times +7, and I'm going to solve this from here. Okay, so that leaves us a 3 plus 98. So my final answer would be 101. So that's term 15. So when we're asked to determine term 15, what we're actually trying to figure out is the value. So there we go. Which term in the sequence has the value 220? Well, that's a little bit more tricky. So we're starting at term 1 is 3. We don't know which term it is. But we know that whatever term it is, it actually is 220 as the value of it. So that's the difference between n and tn. N is just strictly which term number, and this is the term value. The common difference is still the same. We're still talking about the same sequence, so we're still going to be using +7. So you can tackle this a couple different ways. Using the equation, we're still going to just plug and chug. So Tn equals T1 plus n minus 1 d. And we're going to fill things in and isolate n. So we get 220 equals 3 plus n minus 1 times 7. Okay, from here, what we're going to do is we're going to subtract 3 from both sides in order to isolate the term that has my variable in it. So we've got 217 equals n minus 1 times 7. Now I need to strip away what's outside the brackets, so I'm going to divide by 7. That leaves me with n minus 1, and it's equal to 217 divided by 7 is 31. I'm adding 1 to n, right? Or I'm subtracting 1 from n, so I'm going to add 1 to make it be 0, so it's just n left on the right-hand side. And so 32 is my final answer. So it's term number 32 is 220. Is what we're actually saying. Example 3 then digs into, okay, well, what about when we don't actually start with term 1? What if we have term 1, term 2, term 3 not known, and we're left with term 4 equals, I'm just going to change writing this, term 1, term 2, term 3, -4, term 5, term 6, and then term 7 is 23. Well, how do we figure out, can we figure out like the common difference maybe? Okay, so how we actually can do that is we can take the difference in terms, so term A minus term B, where B is smaller than A. So we're going to find the total difference between them, and we're going to divide by the difference of my actual term numbers, so A minus B. Okay, so that's great, Miss Conrad. These are a bunch of extra letters. Okay, A and B are any term number other than term 1. Oh, and A has to be bigger than B, so B is not going to be term 1. But this technically can still work for term 1 as well. So in this particular example, we take term 7 minus term 4 divided by 7 minus 4. So it's going to be 23 minus negative 4, all divided by 3. So that's going to be 27 divided by 3 is 9. So that is my common difference. Once I have my common difference, I can work backwards. Again, either by strictly counting backwards and saying, okay, well, negative 4, I would have had to add to go right. I'm going to have to subtract to go left. Subtract 9 each time. Well, that takes me to negative 13, negative 22, and negative 31. So term 1 equals negative 31. Okay, and we could have used a similar strategy up in part B here. Alternately, if you really love just using equations, they make sense to you, you are totally welcome to do that here. Because we know term 4 is negative 4. So we know n is, term n is negative 4, where n is 4. We also know our common difference is positive 9. So literally that means we know this variable. We know this variable. We know this variable. So we're only left with one that we need to solve for. And we are able to do that. So we plug and chug. Negative 4 equals term 1 plus 4 minus 1 multiplied by 9. So we got negative 4, term 1 plus 3 times 9 is 27. I'm going to subtract that 27 on both sides to isolate term 1. And we end up at negative 31. So either way, I do get the same answer no matter which strategy. Okay. So if we don't like equations, you can think about it in terms of the logistics of what exactly is an arithmetic sequence. How is it all constructed? Now we can run into word problems when we do this type of question. The comet Denning-Fujikawa appears about every 9 years and was last seen in the year 2005. So term 1 is technically 2005. That's when it happened. What is 9? Well, 9 is the reoccurring piece that keeps showing up again and again and again. So that's actually my D value. My common difference is positive 9. Determine whether the comet should appear in 3085. So term n is going to be 3085. What would n be? Again, we know 3 out of the 4 variables in my equation. If I start filling it in, I know term n, I know term 1, I know d. I'm solving for n. So I can actually use this equation. You could also sit there and add 9, add 9, add 9, but when it gets to be these large numbers, that might take a little bit of time. And we want to be as efficient as we possibly can. So that's where the formula comes into play. We've got 3085 equals 2005 plus n minus 1, because we don't know how many times we're going to add 9, how many times that comet is going to pass between these 2 years, but we do know that it should be every 9 years. Again, we are just isolating the variable, so we need to get n by itself. The first thing that needs to go is the completely separate term, 2005. So right now it's positive, so we subtract 2005 in order to get it to disappear. Now we've got 9 n minus 1. And I've just reordered it. Remember that 2 times 3 equals 6, but so does 3 times 2. Order doesn't matter when we're talking about multiplication, as long as the material inside the brackets doesn't change, because adding and subtracting, their signs do matter. So we're going to subtract that, and we get 1,880, and we're going to divide by 9 in order to isolate my material that's in brackets. So 120 equals n minus 1, add 1, that's going to be 121. So in the end, I do need to write a statement because n equals 21 doesn't tell me much. It just tells me that yes, it is in fact part of my sequence because I have a whole number here. If it was a half a number, then it would be like term 2.5. That doesn't fly. That would not be part of my sequence. Therefore, it would not appear in 3085. But because it is exactly part of my sequence, it's going to be the 121st time after, or the 120th time after 2005, so including 2005, 121 times it'll have gone by Earth. That means that yes, it is part of my sequence. It's a whole number. Okay, so whole numbers means it is part of the sequence. So my final statement, because the question is determine whether the comet should appear in 2000 or 3085, my final answer is yes. Not 121. The answer is yes, it will appear. And so that would be my final statement. So I want you to practice some of these questions, really wrap your head around this idea of sequences and series, and then we'll be ready to move on, or the arithmetic sequences rather, so that we can move on to arithmetic series.